Welcome to today's lesson. Today, if you clicked on this, you should be ready for Chapter 10, Section 1, the relationships between heat and work. So if you're following your little guide there for what you're supposed to do, we're at Watch Video. So I assume you've already read the section, um, both of the mini sections underneath section heading 1. Here's some things that you're going to need today. I'm just going to try to summarize. So I don't want to be overly long about this because you can read. I just want to maybe round out some of the concepts for you today. So you're going to need your textbook. I might tell you to look at a picture. You're going to need the Chapter 10 handout packets. The first 7 slides is what you'll be looking at today. And then you're going to need some paper to take some notes that come from my stuff in just a little bit. Okay, so I'm going to go ahead and switch it over to the slide, and yours should look like this, except not in color. Page 1. Here's kind of an overview of the chapter for us today. You can see at the bottom I got my notes, so I'm basically going to read these things out. Section 1 we're going to talk about today, the relationships between heat and work. The next section will be Section 2, and that is about how a heat engine works. And then we'll discuss the cyclic processes or the engine cycle of intake, compression, the power stroke, and exhaust. We'll show you some examples from different kinds of engines, and you'll read an article about some of the alternatives automobile engine setups. And then the third section we'll be talking about entropy, which means that all the energy that we pump into an engine, we don't get it out as work. And then calculating the efficiency of an engine based on some formulas that are derived out of entropy. So that's what we got coming up for this section. Okay. Now let's get into that first section here under the objectives. What we're going to look at today. I want you to do something here. I want you to underline in that first objective where it says on and where it says by. It says recognize that a system can absorb or release energy as heat in order for work to be done on or by the system, and that work done on or by a system can result in the transfer of energy as heat. When we say on, we mean that something is doing work on the system. That indicates negative work. And then when it says work done by something, that's going to mean a positive value for work. And I just want you to write that down in there so that when we come back to that, you'll see what in the world I'm talking about. On the second bullet item where it says compute the amount of work done during a thermodynamic process, here I'm going to show you where we get the formula or where we get the equation that's used to determine work thermodynamically. I'll show you how stuff that we've already done corresponds to that, how it lends itself to coming up with a good, nice formula. And thirdly, distinguishing between volumetric, isothermal, and adiabatic thermodynamic processes. We'll get to that. I'll give you the definition and an example of each of them that might be better than what you might read in the book there. Okay, so here we are. Slide 5. This is your page 3 of your handout. And we've got some definitions. That's what I want to focus on here is just the meaning of these terms. You can see up the top, heat and work. We said that heat's a form of work or can do work, and energy being transferred to or from a system. An object never has heat or work in it. It only has internal energy, which we're going to talk about as a change in U, if you recall that from previous lessons in Chapter 9. What I want you to do beside where it says a system and an environment is I want you to draw yourself a little picture. By system, I want you to draw yourself a picture of a car. Because an example of a system would be like a car's engine, set of particles or interacting components. That's what you're studying. You're studying the pistons, you're studying the intake and the gas, you're studying the exhaust. And so that's considered to be the system. That's where we want to calculate heat. We want to calculate how much work is done. We want to calculate the change in internal energy. But environment is everything else. Environment would be like the rest of the car parts, the hood, the interior of the car, and the air surrounding the cars. Everything that maybe like if you lose heat, that's where it's going to be lost to. You know, you feel the hood after you've used the car for a while and it feels warm. That's part of the environment. That's part of where the energy gets lost or unusable. So everything in the problem that is not the engine is the environment. All right, I wanna look next at where in the world they get this stuff. That's your page 4, I believe it is. I'm gonna flip over to my handwriting page, and this is where you're gonna want your paper out so you can take notes. Remember, you can pause me at any time so that you can get all this stuff down. Okay, I got kind of like one and a bit page for you here to describe where this stuff comes from. So the whole deal with thermodynamics and why thermodynamics is cool is because we use expanding gases to do work. We know that's what happens inside of your engine. Internal combustion engine, diesel engine's a little bit different, but we got the same idea here. Or steam engine, it works on this principle. We'll look at, I guess I should start maybe up here with an adiabatic process, but I didn't. I'll go down here and just say we got expanding gases that can do work. We have some types of thermodynamic processes that this one's not in your book. It's called isobaric, or same pressure, like barometric pressure. And we start with this picture over here on the left. You got a piston with some gas in it, and then you increase the temperature in there. Usually in a car it's by the spark plug, and boom, up goes the piston. It increases the temperature, and so the gas does work on the piston so that now the piston is raised. The volume increases of the gas inside the piston, but the pressure stays the same. That's why the thing slides. If it's lubricated well, then the piston will go up. Okay, so the pressure should stay the same. Graphically, this is what it's going to look like. You got on the x-axis, you got the initial and the final volume. And on the vertical axis, on the y-axis, you've got the pressure. And we already said the pressure stays the same, so my line goes straight across. The work can be calculated. The work done in that piston can be calculated by taking this side, the x side, multiply it by this side. Or, in fact, it's the area under the curve in the picture here, which is pretty easy to calculate. It's just a matter of area in this case. So pressure times a change in volume is the amount of work that's done. The change in volume in this situation is the cross-sectional area of the piston, the circle there that I'm pointing to right here, times the distance that the piston moves from the before or the initial stage to the after stage. That space in between there represents the volume, the change of volume when work was done. Okay, now here's where we get the derivation of the formula. In addition, the force acting on the piston due to that pressure exerted by the gas, it pushes up, but then the pressure stays equal. On the area A is F equals P times A, pressure times area. This is just another form of what we used in Chapter 8 for pressure when we were dealing with Pascal and whatnot, that pressure equals a cross-sectional area force over a cross-sectional area, so you could lay down on the bed of nails and not hurt yourself. If I move the pieces around, multiply both sides by A, I get pressure times area equals force. Also, work equals force times change in distance. We learned that from chapter, I think it's 5. And so if we substitute F equals PA into the equation for work here, we get work equals P times A times delta D. And as shown above, A times delta D is the change in volume. So a formula for work could be pressure times change in volume. Now, if the pressure of the gas changes during the expansion, it gets a little more complicated. We get a picture like this, and finding the area underneath a curvy curve like that is going to require calculus to help us out. And, you could do that when we get to the end of our pre-calculus book. The point there is that's where that comes from. And this might be a point where you want to stop and pause and go ahead and try the practice problems, practice A on page 338 that you're supposed to do for homework, or you can wait till I'm done with this and go ahead and look at those. I just got a little bit left to talk about here, where we switch over to looking at the definitions or examples of those last other processes. Okay, so I got other stuff coming up for the next section that are down below. What I might do here is then, if you go to the next slide, if you go to this one here, that's basically explaining what we just did. This one as well. The next slide, your pages 5 and 6, I guess it is. That just explain what I just talked about. What I really want to look at now is we got these 3 thermodynamic processes that you've read about in the book. Isovolumetric, same volume through the process. Isothermal process, and adiabatic. You can see at the bottom I've given you examples of those 3 things. A bomb calorimeter or a pressure cooker is an example of an isovolumetric process. You're still adding heat, you're adding energy to the system, but you're not getting any change in volume. An example of an isothermal process is when they send up a weather balloon. As the pressure changes in the environment, the pressure on the inside of the system increases, but the temperature stays the same. So a weather balloon is an example of isothermic, and a dust spray can or a fire extinguisher is an example of an adiabatic process. Something happens really super fast. There's no chance for any energy to be transferred as heat, but the canister itself gets really, really cold, and sometimes ice condenses on the outside of it. Maybe you've experienced that by using a fire extinguisher at work or something, but I have a dust spray can here at school that I use kind of as a demonstration. Okay, now hang on. Here's a demonstration that'll talk about each of these three kinds of things and give you a little example about this. Just listen up to the lady.
An isovolumetric process is a thermodynamic event that takes place at constant volume so that no work is done on or by the system. An example of this process is what happens inside a bomb calorimeter. A small quantity of a substance undergoes a combustion reaction, releasing energy and increasing the temperature and pressure of the gaseous products. The walls of the container are very strong, so there is no change in the volume of the gas. The energy is transferred only as heat. Now we will consider a process in which temperature is held constant. The word for this is isothermal. A close approximation of this process is if you were to carry a sealed balloon up the stairs of a very tall building. Since the air pressure drops gradually at higher altitudes, the balloon will expand. The balloon is growing even though there is a pressure force pushing inwards against it. Therefore, the balloon does work and it should lose internal energy. If nothing else happened, the balloon would cool off because of this. However, since the temperature of the outside air is warmer than the cooling balloon, energy enters the balloon and keeps the two temperatures identical. Therefore, the balloon neither gains nor loses internal energy. The energy transfer and work done are simultaneous, and so the process is isothermal. An adiabatic process is a thermodynamic event during which work is done on or by the system, but no energy is transferred to or from the system by heat. Consider inflating a balloon very rapidly. There is no time for energy to be gained by the gas in the balloon. The internal energy of the gas decreases because the balloon did work while expanding. Adiabatic processes usually happen quickly or inside well-insulated containers.
And that's it, okay? So if you go and you do practice A now on page 338, you finish those 4 problems. They should be pretty easy, and you're done for day 1. Good job.